Um, I think, I'll be going over research we're doing in the research group and then talk about some ongoing research related to just improving these methods in general. So these are the students in the research group, which is Regina, she's right there. And I'll go over some background and then I'll talk about how we are able to solve pathfinding problems using reinforcement learning and A-star search. I'll have to skip over the second bullet point because I won't have enough time. And then I'll talk about ways we are trying to generalize these solutions. So instead of solving just one particular problem, how can we generalize them without having to retrain our heuristic functions? And then I'll talk about some applications. And if I have time, I'll talk a little bit about some future work. So what are the classic problems that we're looking to solve? The classic problems we're looking to solve is called pathfinding problems. And the objective of a pathfinding problem is to find a sequence of actions that forms a path between some given start state and some given goal. Just some feedback. And some given goal, okay. That where a goal is a set of states that are considered goal states. And the also one of the preferences for pathfinding problems is to minimize the cost of a path. So you can represent a pathfinding problem as a directed graph. And we can say the nodes here represent states in our state space. The edges represent actions, and the edge weights represent transition costs. And the goal is to find a path, but not just any path, preferably the shortest path. So for example, this here is the shortest path. It has a path cost of 3 from the start state to the goal state. So this is how we can represent pathfinding problems. Now, pathfinding problems are found all throughout computing, mathematics, robotics, sciences. They're everywhere. In fact, writing an algorithm itself is composed of a pathfinding problem. And I would argue that artificial intelligence in general is just meta algorithms that write algorithms. So I think this is key to solving AI. So for example, synthesizing circuits for quantum computing, getting robots to do pretty much anything, doing program synthesis, proving theorems, solving puzzles, synthesizing chemicals. These are all pathfinding problems. Now, the size of the state space of these pathfinding problems can be very large. So 10 to the 60 may be something that you see, but even this for like say organic chemistry, it's probably much larger than 10 to the 60. So you can't brute force these solutions. But what we assume that we know is we know what actions we can take. We know what happens when we take those actions. We know the costs of taking these actions. We can test whether or not we reached a goal state, and we have some language with which we can specify goals. So the objective then is, given this, can we then use AI to solve any given pathfinding problem? That's our research objective. All right, so then the question is, I said any given pathfinding problem. Well, what exactly is this going to entail? Is this really going to be any pathfinding problem? Well, here we're working with deep neural networks in order to do this. And with deep neural networks, you assume that you have sufficient amount of data. You assume your network is expressive enough to learn the problem at hand. So you're going to need a lot of data. We know deep learning is data hungry. Now, there are certain problems where it's really easy to generate data because you can do this all in simulation. So, theorem proving, program synthesis, quantum algorithm compilation, you can just, generate data. It's fine. You can generate billions of examples. There are other environments where you can generate data. The data might not always be precise, but there are methods to account for that. So for example, with chemical synthesis, you can simulate what will happen in chemical reactions. For robotics, there's things called sim to real, where you do something in simulation and then try to transfer it onto a real robot. And if it's in simulation, you can gather a lot of data in simulation. And Of course, there may be some niche problems where data collection might be really computationally intensive. And so what we then would want to do in this case is learn some foundation models that can generalize across domains. So you can solve problems across maybe thousands of different domains, and then you're given a new domain. And maybe you can solve this problem without even actually having to retrain or anything like that. Maybe you can solve this problem right off the bat. So for example, if you train yourself to solve a bunch of different puzzles, like a Rubik's Cube, or sliding style puzzle, these different kinds of puzzles, and someone gives you a new puzzle, you may be able to solve it really quickly. Whereas if someone just gave you the new puzzle and you hadn't solved any of those older puzzles, you might struggle. Okay, so let's talk about the first approach we have for solving these kinds of problems. And this is going to be a combination of reinforcement learning and heuristic search. Value iteration is a core algorithm in reinforcement learning. And the way value iteration works, or rather I should say, what value iteration is doing is value iteration can compute the cost of the shortest path for every state in your space. So if you're able to fit everything into a table and you run value iteration, you're guaranteed to converge to H star, which is the cost of the shortest path. So at any given state, what's the minimum cost that I need to incur to solve that problem? So for example, if you could do this for chemical synthesis, which you can't in a table because it's too large, but if you could, you would know the minimum cost you need to synthesize any possible chemical. So here's a visualization of this working. Here we have this pathfinding problem where you're trying to get from here to the shovel. You don't want to run over rocks. You don't want to run over plants. And this is running value iteration. And you can see these arrows are obtained by just behaving greedily with respect to the value function. So I'm training my value function, and then I'm just seeing every action it can take and what is going to be the lowest cost action, and I'm going to then take that action. And after this converges, we can see that if we just greedily follow this value function, then we can find the shortest path to this shovel. So this is just a visualization of how this works. Okay, so like I said, you're not going to be able to fit everything into a table. And so what we then need to do is we need to turn to approximate value iteration. So instead of representing our value function as a table, we can represent it instead, say, a neural network. And we can then do this value iteration update that we did with the table, but approximate it with a neural network. And so you see here, we're training our neural network with parameters theta via some mean squared error to match this value iteration update. And we can repeat this process over and over again, and hopefully we end up with a heuristic function that approximates H star within a range such that we're able to reliably solve problems and hopefully solve them efficiently. Okay, so the first tests that we did with this were on different kinds of puzzles, like the Rubik's Cube, these sliding tile puzzles, this lights out puzzle where if you press a square, it turns it on or off. And same thing with the ones immediately adjacent to it. And the goal is to turn all the lights off. And the soccer band puzzle where you're this green agent and you want to push these boxes onto these targets. All right. So the way we initially did this is we started from this goal, and we could then take steps in reverse from the goal, which for the Rubik's Cube is trivial because it's a reversible domain. But the reason we want to do this is in order to learn to solve these problems, we need to see problems of varying difficulty. So we can easily generate states that are closer to the goal or further away just by scrambling the cube a certain number of times. And we use a neural network. We use essentially the same architecture for all of the different problems. And we use the same training process for all of the different problems, mostly for all of the different problems. And for our results, first we wanted to see what would happen after training this neural network if we just behave greedily with respect to our heuristic function that we trained with value iteration. And here we have on the x-axis training iteration, On the y-axis, the percentage solved by just the greedy policy. And each one of these lines represents a cube that was scrambled a certain number of times. And you can see that after about scrambling it about 10 times, it is not reliably solving it 100% of the time. So 10 times, maybe 95% of the time, but then that goes down over time. And it stops being able to reliably solve all the states. So what do? We then turn our attention to heuristic search. So we train this heuristic function, and we can easily use this in heuristic search algorithms. Now, these heuristic search algorithms are able to search state space by prioritizing which states they look at according to the estimated cost it would take to solve the problem by going through that state. So what it does is it says, it says, given some current state that I'm looking at, what was the cost I took to get there? So what was my path cost? And what's the estimated cost to solve the rest of the problem? And that comes from the heuristic function. What's my cost to go? And it prioritizes the nodes it looks at using this cost function. And what was I going to say? Something else I wanted to say about that. Can't remember. And we do this modified version of this search to account for the fact that our heuristic function is a deep neural network, it's computationally expensive, and so we can look at multiple states at a time instead of just one at a time, as is typically done to speed up our search. So we call it batch weighted A-star search. Okay. And so here are the results for solving these different puzzles. And with some of these, we can verify the cost of the shortest path using these particular domain-specific solvers. Like for the Rubik's Cube, they have these solvers that use symmetry and group theory math stuff that I don't totally understand. So in some of these, we can verify the cost of the shortest path. Now, for all the test instances, we were able to solve them all 100% of the time. And for something like the Rubik's Cube, we solved it optimally 60% of the time, 24 puzzle 96% of the time, lights out 100% of the time. We did this on the order of seconds, but you know, the interesting part with this is we essentially use the same algorithm, this whole DQA algorithm. We use the same algorithm to solve all of these. And we didn't have to give it any information about how you should solve it. So for example, like I could solve these puzzles, but I couldn't solve this puzzle. This puzzle was actually surprisingly hard. I actually couldn't solve it myself, but the thing figured out how to solve it for me. So I didn't have to think about it. And that's what AI is all about, not thinking about stuff. It's about writing algorithms that write algorithms for you. Okay, I don't have the time to go into this, but this is, if you have a lot of actions, you know, search can be slow and we modify things so that search is faster, even if you have a whole bunch of actions. Okay, so now let's talk about generalization. So we saw that we had to train a neural network just for solving the Rubik's Cube, just for that one Rubik's Cube goal state. So I just want to reach that one goal state. I have to train a neural network for that. But what if I want to reach some different goal state? So you could think, for example, with chemical synthesis, I can train a neural network to synthesize one chemical, but what if I, you know, then want to synthesize another one here? I have to train it from scratch. And with the previous algorithm we presented, the answer is yes. And that would take, you know, in our experiments, between half a day to 2 days to train. So if you have like 1,000 different problems you want to solve, that's a lot of training time. It's not practical. So we do want to generalize over goals, but then we'll also talk about how we can generalize over domains. So we don't have to retrain one for like the Rubik's Cube, the sliding tile puzzle, so on and so forth. And then generalize to when we don't know actually what the transition function is. Say we're working in the real world with a robot, we don't exactly know what's going to happen next when we take this action. Can we still use these algorithms? Are there any questions? So here is an overview of our method for generalizing over goals. Like I said, with the Rubik's Cube and these other problems, we started from the goal and we worked backwards. This isn't always going to be possible because not all environments are reversible. So I can't, you know, necessarily like break something and then think about what would happen if I go backwards from that. So we want to then generalize this also to domains that don't have these reversible action spaces like the Rubik's Cube. And so we build on what's known in reinforcement learning as hindsight experience replay. So for example, I can start from some start state, wherever that is, take some sequence of actions, and wherever I end up, I can pretend that that's my goal. And so then I can generate pairs of start states and goal states without having to think in reverse. Just by taking some actions and wherever I end up, that's my goal state. And then to allow for the description of more complex goals. So maybe, for example, I have a goal where I know what kind of chemical I want to synthesize. So it should have these properties, it should be soluble in water, it should bind to these receptors, so on and so forth. But I don't actually know what that chemical looks like. So this is known in chemical synthesis as the optimization, molecular optimization. But I might, I might not be able to actually find a chemical just by thinking about it that meets these properties. So can I just specify instead the high level properties and be able to find, be able to find a path to some state that meets these properties. And so instead of giving our deep neural network the start state and a goal state, we give it a representation of a set of goal states. And so assume that there's some way to translate this state into a set of descriptors. And then we can use all the descriptors or some subset of the descriptors. As long as the state is a member of that set, it's fine. We give that to our neural network and we do our reinforcement learning. And then later on, we also are going to assume that we can use some specification language, whatever this is. It can be formal logic, it can be natural language. But as long as we can translate that to our goal descriptors, we should be able to find paths. Okay, so let's then zoom in on the Rubik's Cube and see how we do this with Rubik's Cube. So the way we're going to represent the state to allow us to specify not just any state, but a set of states, is we're going to assume that we know all the stickers, where they are, so there are 54 stickers. And when we specify a state, we're just going to specify the locations of the stickers. This is like we did before. But say, for example, there are some locations of the stickers where we don't care about where they are. Well, we can then assume that we can just not assign stickers these locations a particular color of sticker. And therefore, some of these can be unassigned. So in general, for any domain, we assume that there are a set of variables and that a complete assignment represents a state. But we could have some partial assignment, like we have here, where I say I only care about these stickers. The rest of them I don't care about. And so this, for example, if this was representing a set of goal states, this would be a goal state that satisfies this criteria. So then this allows us to represent sets of states instead of just a single state. All right. And so here's our training loop. This is a subset of the image I showed you before. So we take our state and we look at all the stickers that were assigned colors in the state. So there are going to be 54. And so then when we give this to our deep neural network, we can give it all 54 assignments or some subset of this assignments. And it's going to learn to find a path to a closest goal state in that set of states. So these experiments, this is more like planning people would care about this, but this is just to show that our approach for doing this is better than other domain independent approaches. So if you don't make any assumptions about the domain, then our approach using deep reinforcement learning and A-star search works better than other people's approaches. Sometimes significantly better, like between like some other approaches solving like 1% and ours solving 100% cases. That's more like people stuff. Now, as I said before, there was a way to build on top of the way we specify goals using some specification language. So like I said, the way we would specify goals is with a partial or complete assignment of values to variables. So for the Rubik's Cube, we're assigning colors to the stickers. And this is going to be the same for all the different domains you look at. It's just some assignment of values to variables. Now, we may have more higher level information we want to communicate, but are not sure how to communicate this as just values to variables. And what we can do is we can use formal logic to actually specify our goals. And then we can use what's known as answer set programming to translate that formal logic into some partial assignment to represent our goal. And like I said, the logic we're using is called answer set programming. I won't go too much into the details of answer set programming, but the reason we use answer set programming is we can define properties about a problem using only a few lines of code. So for example, if I want to say, describe the canonically solved Rubik's Cube, I can say for all 6 faces, they should all have the same color. So this is what that face saying, I'm saying there's 6 of them. And then for the face saying, I'm just counting all the stickers and I'm saying that they all have the same color as the color of that face. So with the white face, there are going to be 9 white stickers on that face, for example. And so just with these 2 lines of code, I can specify these goals. And so this is why we're using this answer set programming, this particular logic programming. But it doesn't have to be ASP. You can translate natural language to partial assignments, then you can use that. But ASP happens to be just very convenient for us. Now, this answer set programming then is going to define a set of goal states. So here in this black dot, assume this is where I start from. This is my start state. Assume this red, so assume this circle represents the set of all possible states. This green is then going to represent a set of goal states. And I then want to find a path from this dot to state within this green here. But like I said, through pathfinding, we also care about finding shorter paths instead of longer paths. And so a path that goes, assume we're in Euclidean space and shorter path relates to a shorter path in Euclidean space. I'm going to want to find something closer to the edge here instead of maybe something all the way in here. So I'm going to want to find a shorter path. Now, with this answer set programming, there can be multiple different partial assignments that are going to satisfy this program. So for example, I could sample one of these partial assignments and it can be further away from the start state. I could sample other partial assignments that are closer to the start state. And we then would, of course, prefer the ones that are closer. And so one thing we can do to address this is we can sample multiple different partial assignments and pick the one we think is closest and then try to find a path to that one. Now, another technical thing here is the way, this is a formal logic thing, but any of the assignments that we get are going to be guaranteed to represent some subset of the set of goal states. So that's what is known as monotonic behavior. They'll never represent something that is not a goal state, but we can actually use this, we'll use this a bit later to our advantage. Okay. And so in formal logic, like I said, we have this non-monotonicity. So for example, what non-monotonicity is I can retract something that I previously thought was true by getting more information. And so for example, if I say that it's not raining, the way these logic programs work is they first try to prove that it's true, like prove it's raining. And if it can't prove that it's raining, then it assumes that it's not raining. So it's just saying, if I can't prove it, I'm going to assume it's not true, which of course isn't always going to be the case. So for example, I can specify that I want this white cross, but I want there to be no yellow sticker on the white face. And you see here, these gray represent just, they can be anything. So these actually could be yellow, but since they're grayed out, they're not committing it to be yellow. And so at first it's going to try to prove, is there a yellow sticker? If it can't prove it, it'll assume that, hey, this isn't yellow. So I'm going to assume this is true. So this is the kind of goal that we would give it, but this is still a member of this set of states, even though it has yellow sticker on the face. And so this non-monotonicity then presents a problem if we're trying to solve these kinds of problems. I want to synthesize a chemical with these properties, but not these properties. So this kind of problem is going to come up frequently in the real world, and we have to find a way to deal with it. Now, there are a lot of technical reasons why specifying not something is very difficult for computation, because like there could be infinite things that are not this thing. And if you know, it's just computationally inconvenient to represent that. So by just saying, I'm going to try to prove that it's true, and if I can't, then it's not true, is very computationally convenient. But we can handle non-monotonicity by instead trying to find a path to a goal state. So for example, I can specify something that actually, if I don't assign anything, any values, then it actually happens to be true. And so, for example, this could be as large as the set of states itself. And so this could be my set of states where, of course, I don't have to find, I don't have to take any actions because the start state is included in it. And it could then say, okay, I found a path, but remember, we can check whether or not something's a goal state. So we can check and say, okay, that's not a goal state. And then I can refine this set of states and say, well, let me look for a subset of this. And then I find a subset of this, I find a subset. But the problem with this approach is that this subset here does not take into account why this state, this path that I found actually was not a goal state. And so, for example, I can still get the start state as a potential goal state, even though I've already known that there's no way it can be a goal state. So it doesn't take into account why this is, and we'll talk about how we can overcome that in a second. But before we get to that, I just want to talk about some of the results we have for these different specifications. So for example, I can specify that I have 6 crosses on the face of the Rubik's Cube. I don't care about anything else, just give me 6 crosses. Now, of course, the canonical solve state also implicitly has these 6 crosses. But you can see here that the path cost for the 6 crosses versus the canonical one is actually much smaller. And the reason for this is this 6 crosses represents a larger set of states. And so we can see that this is learning not just to find a path to a state, but learning to find a path to a closest state in that set of goal states. So if I specify something more general, I should be able to get a much cheaper path, not a much cheaper, but at least as good as more specific one. And so this is showing I can get cheaper path costs by specifying things that are more general. And then I can find paths to these different patterns, and I can specify them using just a few lines of code in logic programming, and I don't have to retrain my deep neural network at all. So that's really the take-home message. There are, you can essentially get to any possible state in the Rubik's Cube state space from any other possible state without having to retrain your deep neural network. And then similarly for this soccer band, I can specify things like make a box of boxes, push all the boxes into a corner or something like that without having to retrain my network. Now, like I said, with this non-monotonicity, it's very important to take into account why something wasn't a goal state. So I find a path, but it's not a goal state. Why isn't this a goal state? And if we take into account why, and then refine our search, we can then get a subset that doesn't include that previous state we had before that no longer was a goal state. And we can find another path, say that terminal state isn't a goal state, where we can refine it again. And hopefully this will result in us finding paths a lot faster. And we can see that this is indeed the case. So for example, I can specify that all the stickers on the white face should be different than the center sticker. And I can specify this in different ways. I can specify this I can specify this monotonically by saying all the stickers are, and I can positively say that there exists 9 stickers and each sticker is different than the white cubelet. Now, the problem with this is in order to specify this as a goal, I have to find assignments of values to these 9 stickers. And so I have to actually go search, solve that problem, find assignments of values, but not all of them are even going to be possible for me to reach. I could specify something that's impossible for me to reach. And so this takes a lot longer and results in you finding a lot higher path costs. Whereas with negation as failure, it's much faster. Say, for example, with this sliding tile puzzle, I should say, I want to say all rows sum to an even number. So that I can specify monotonically, or I can say there does not exist a row that whose sum is odd. So these are the same set of states. It represents the same set of goal states. But I can reach this one a lot faster and be at a lot shorter path cost than the monotonic. So in this work, we can exploit this non-monotonicity to find goals a lot faster. And one of the reasons is I don't commit to certain things being true initially. I don't really commit to much being true. I try to find a path, and if it's not a goal state, I can just commit to certain things being true that make it so that that last failure case doesn't occur again, and then try again. And so I have fewer assumptions that I start with. And I just build assumptions based on the previous failures that I've had, instead of starting by assuming all of these different things are true. Okay, now we'll talk about generalizing over domains. So you still have to train a separate one for the Rubik's Cube, for the sliding tile puzzle, just like the band. Even though you can generalize over goals, you still have to train a new deep neural network for each one. So can we actually generalize over domains? Now let's look at this sliding tile puzzle here. So if I'm only using the canonical actions, meaning I can swap the blank tile with the ones immediately horizontally and vertically adjacent to it, then the cost to go here is 16. But if I include the diagonal actions, the cost to go is actually 2, because I can just move it diagonally, and this is going to be solved a lot faster. Now, just by looking at the states, of course, I don't know this. I have to have some information about the domain. And so there has to be then a heuristic function that takes into account not just the state, but also the rules of the domain. So it can differentiate between these cases. And we train it very similar to how we do before, except the heuristic function is given also this domain information. Okay, so this work is done with just varying different sliding tile puzzles and just randomizing the rules of where you can swap this blank tile with the sliding tile puzzle. We have some other more new results that are more general than this, but I'll just talk about this for now. And so it's just trained on these sliding tile puzzles with different kinds of domains, rules for that particular puzzle. And so we can see that giving it information about the domain. So in these charts, the x-axis is the ground truth cost to go. The y-axis is the output of the neural network. So if we don't give it information about the domain, it performs a lot worse than when we do give it information. So this shows that it's making use of that information about the domain. Here, I'm going to skip over this. This is interesting. But what we see in these charts is that we have DeepCube. This is the one that's trained for that specific domain. And then we have our method. And our method is more general than DeepCube. We only have to train it one time. But of course, because it's more general, it's going to be learning a more complex function than what DeepCube is learning. So it doesn't perform as well as DeepCube at solving. It performs worse. But the takeaway message here is it's actually able to solve 100% of all the states, like 100. Yeah, it's able to solve 100% of all the states, even though it's never actually, probably has never actually seen this particular domain. It's still able to solve 100% of them without being retrained, whereas with DeepCube, I need to retrain it every time. Now, there's some more general work we're presenting it at a workshop, and here we have this generated models of different domains. You just generate domains on the fly. You train your heuristic function on that, and then you test it on a bunch of different domains, not just sliding tile puzzle. And we see that it is able to solve more than other domain independent approaches. So it's kind of the takeaway message there. Okay. And then I have some time, because about like 5-10 minutes for questions. Okay. Now, what if we actually don't know the rules of the domain? So before, we're assuming I know I'm in the state, I take this action, I know exactly what happens next. But what if we don't know exactly what happens next? And this often shows up in things like robotics. What can we do? Well, there's a whole bunch of literature in reinforcement learning called model-based reinforcement learning, where you're learning the model as well as learning to solve the problem. And we're building off some model-based reinforcement learning ideas. The difference is we want to use this model in heuristic search. Now, there's a very important thing I have to be able to do in heuristic search, where I have to be able to re-identify states. So if I'm searching, I'm trying to find a problem, and I see, oh, I've already seen this state before. I don't want to then look at it again unless I found it via a cheaper way. I found a cheaper way to get there. So this is very important, because if you don't have this ability to re-identify states, the chances that your memory and time grow exponentially, not chances, but your memory and time, the time that you take grows a lot more than when you can re-identify states. Now, the way we do this, so assume our states are represented just as pixels. It may be really hard to then say like these pixels are about the same as this, but perhaps the problem we're trying to solve has an overall discrete structure that we can represent. So for example, the Rubik's Cube is overall a discrete problem. But if we're just given like pixels of the Rubik's Cube, then maybe this isn't as going to be as easy for us to deal with. And so what we do is we have some encoder, we have some decoder, and we give the state to the encoder, and we then convert it to some latent space. And this latent space we actually discretize. So it's only zeros and ones. And we have the decoder to ensure that this latent space actually represents something that's going on in the state space. And then we are learning a model to go from one discrete state to another discrete state. And so hopefully after we're done learning, we can just get our start state, translate it to some discrete state, and then only operate in this discrete latent space so we can do our heuristic search. And we do this on RGB images of the Rubik's Cube as well as of Software. So we're only giving it the RGB images. We give it a limited set of states for training, and it trains itself on these states to predict not the next RGB image, but rather the next latent state. And we see, so we see here that if we just train it to directly predict the RGB images, we actually accumulate errors. So you can see these are the errors accumulating over time for the number of steps you take for the Rubik's Cube. And this is the error, and this accumulates for the continuous one, but not for the discrete one. And for the discrete one of the reasons it does not accumulate is because we can correct for small errors that we make by just rounding. So as long as the error is less than 0.5, we can round and we won't have any errors. Whereas with the continuous one, if you make tiny, tiny errors in the pixels as you're predicting them, these accumulate over time. And so this has been a big issue for deep reinforcement learning when you're doing model-based RL stuff. And we can see with our model, this DeepCube AI, we're able to solve almost every single test state. We can see here that for the Rubik's Cube, where we reverse the start and goal state, we miss one. And so that's 99.9%. And this also does slightly worse. It does worse than DeepCube A. But the difference, one big difference here is this is generalizing over start and goal states, whereas DeepCube A only has to worry about that one goal state. But also, DeepCube A, of course, doesn't have to learn a model, whereas this one does. And so, I also want to say that the heuristic function is trained after learning the model. So you learn the model, you train a heuristic function just on the latent states, and then you do the search in the latent space. So after you learn the model, you don't actually have to get any more real world examples. You train your heuristic function and you search using your latent space. Okay, now some applications. So for chemical reactions, they follow these steps called reaction mechanisms. And you can pose this as a pathfinding problem. Here are my starting material, here are my products. What was the reactions sequence of reaction mechanism steps to reach the products from my starting material? Now, actually figuring this out as a chemist may require a lot of expertise. And of course, there may be some where people actually don't know what the reaction mechanism steps are, but this is actually very important for one, if I'm trying to design certain chemical reactions, I want to validate, are they actually possible? And one of the ways to validate that is with the reaction mechanisms. If I want to synthesize, certain drugs for, say, like treating some ailment like diabetes or something like that, before I actually do any of the experiments, I need to know, like, can I actually do this? But even if I can do the experiments, there are ways I can make it more efficient by knowing what the reaction mechanism steps are. So if you want to make treatment for diseases cheaper, knowing what the reaction mechanism steps are oftentimes can be very important. Okay, and so we can then apply this same DQA approach with the hindsight experience replay, so we can generalize over goals. And this is some technical stuff about what we're doing. But the overall concept here is we're operating, again, with this DQA approach. We represent the molecule to the neural network using what's called a fingerprint. And this fingerprint has some issues with it because it's some predefined way to translate a molecule to some fixed representation. And so we're working with using transformers instead, so that we don't have to actually, with this fingerprint, you lose information. But if we're working with transformers, we can directly give it the chemical formula so we don't lose that information. And so what we have here is some preliminary results, but we see as the number of steps increases, the reliability of us being able to find these reaction mechanism steps decreases. But we see that this works better than if you're just trying to brute force solutions or use heuristics. These are some fixed heuristics based on similarity. So it works better than the fixed heuristics. The learned heuristics works better. Now, one of the reasons I think it's not doing so well, like at steps 4, 5, 6, is just the representation is such that you'll get these collisions where two different molecules look exactly the same to the neural network because of the fingerprints. The fingerprints are exactly the same. So that makes search really hard because you're essentially blind when you have these collisions. And so using a different representation, I think we'll get much better results. Okay, I have a couple more minutes left. Another pathfinding problem, which I wish I had thought of, but these are actually other researchers building off of our work, is compiling quantum algorithms. So if I have some algorithm in quantum computing, these algorithms can actually be represented as matrices. And I then want to find a sequence of these elementary gates to implement that algorithm. So how can I find a sequence that translates this matrix to this other matrix? And people then use DQA to figure out how to do this. And here's them using DQA to train what's known as a deep Q network, and then using this heuristic search method we came up with called Q-star search. I don't have time to get into it, but it can work a lot faster. But what they show is that they're able to synthesize these circuits, and they're also able to synthesize them. I can't remember the exact results, but they had some results for accuracy that they can do better than some approximate methods. But also another important thing for this is some of these gates are more expensive than other gates. And being able to find gates that are cheaper can yield algorithms that are more efficient. And so the cost of the gates can also matter as well. And I have, we're in my research group working on actually how can you do this for any given gate set. So this is for a particular gate set, for a particular number of qubits. How can we generalize this to any given gate set? Okay, some more quantum computing stuff. All right, so that's all. Thank you. Are there any questions?
So basically, anything you represent as a pathfinding problem or other limitations to that?
Um, in problems where you can't specify what the goal should be. So for example, there may be, let me think of a good one. So there may be some optimization problems, like how can I lay out a circuit layout? How can I lay out a circuit that minimizes my power consumption? Now here, I don't know what the actual circuit looks like, but you can translate that still into a pathfinding problem by just the specification I just gave being the goal, and there being a set of circuits that meet this goal. So you can still translate this back into a pathfinding problem. Now, whether or not that's the best way to look at it is debatable, but I do think almost any problem in computation can be posed as a pathfinding problem. It might not be the best way every time, but I think a lot of times it is. Any other questions? Thank you.